Welcome back to ECE 441A, 541A. Few announcements. Homework number 3 is due on Monday. If you need help finding or choosing technical electives, this is obviously for the seniors. There will be, I think, a technical elective info session Wednesday night at 5:30 in room 530. So I tried to make it as non-confusing as possible. Exam number 2 is a couple Fridays from Friday on the 21st. And lab number 2, apparently everyone is bothering Kurt on when are we going to be allowed to do number 2, or when start going to post stuff for lab number 2. I'm glad that you're so excited for lab number 2, but we need to wait until we have a little bit more information from chapters 4 and 5. We'll finish, I hope, chapter 4 today and maybe start chapter 5. Today what I want to do, we talked about sensitivity last time, and we were talking about a transfer function sensitivity with respect to a parameter. There's also 2 other functions that have been defined, and we want to define those today and try to understand what those represent and illustrate that this actually is one of the cases where you have a trade-off. Control theory is sprinkled throughout with trade-offs, and we have to figure out or decide how do we make these trade-offs in our design process. We'll then work through a sensitivity example, finding the sensitivity of our overall transfer function with respect to a parameter alpha. And then we'll look at another formula or an expression for doing that and use that formula to basically check the work that we just finished. And then we'll have some more review, Bode plots. We'll have a function that's a function of frequency, and we want to know what does that look like as a function of frequency. And for that reason, we want to sketch its Bode plot. The Bode plot, then, you need to start getting up to speed on that because we'll be using that in our design later on in the semester. And as I said, maybe we'll get to chapter 5, but I sort of doubt it. But that's on design specifications. How do we relate these S-plane pole locations to time domain performance specs? Again, I can't emphasize this enough. The control is based on trade-offs, and today we're looking at one particular trade-off, and that's between the sensitivity function and the complementary sensitivity function. To understand that, I'm going to scroll through this rather quickly. You have these notes available to you after class, and I'm trying to reference those where they occur in the textbook so that you can refer to those if you want to. But this is the block diagram that we're interested in today, and you can see that we have many, many different inputs, not just the reference input R. What other inputs do you see? T sub D is a disturbance input, which if we were a cruise control on an automobile, what might be a disturbance input? If we're worrying about steering, we might have curves. That might be considered a disturbance, but I was thinking in terms of speed. Now we might have inclines up or down that might then present a disturbance signal to our controlled system. N is luckily using the letter N for noise. That could be a sensor noise, and you might now have sensor noise added onto your measurement, and that actually now gets fed back in as you're comparing your filtered output Y filtered through H with your reference input R. In this particular class, we will usually go ahead and set H equal to 1. And if it is, then this E sub A, if the noise wasn't present, would look like our tracking error. Our tracking error is defined as the difference between where we want to go, our reference signal R, and where we actually go Y. And here I've just labeled what some of those particular signals are. Our reference input R, that's the one we're familiar with, our measurement noise N, and the disturbance T sub D coming in between our controller and our system, or between our plant and controller. Just to make things easier, we'll reduce our writing to one letter instead of two with some subscripts maybe. We'll define this loop gain, L, to be all of those transfer functions in our loop, G sub C, G, and H. And in the textbook, we typically will just go ahead and let H, we won't introduce any sensor dynamics, we'll just let H be 1. And that says then that our loop gain is this product, this cascade combination of our controller and our plant. So L is just an abbreviated form of G sub C and G, the product. And what I want to do now is try to unpack where this is coming from. This is our tracking error, the difference between the reference input and the output Y. And obviously it has three different parts. Three parts coming from the three different inputs. We have our reference input, our disturbance, and our noise. And we'll talk about S and C in a little bit. But what I want to do now is actually have you derive, which one do you want to derive? Pardon? That's not the response I was looking for. Oh, you were meaning we didn't have any response because we didn't have any, we had nothing for the noise, right? Yeah. We need to do this at least once so that you get a feel for where these pieces are coming from. And what do we know since we have a linear system? How can we solve this? The trick is to just, let's find the transfer functions between one of these inputs and the output Y. And this is going back to what you've already done on your exam. You should have been able to do this based on exam number 1. Let's find the transfer function between the disturbance and the output Y. And how do you do that in this particular environment if it's a linear system? What's the first thing that you're sort of utilizing? One property. When we have linear systems and we have multiple inputs, do you remember what the word is that we sometimes use? Superposition. We want to use superposition to try to find the transfer function between T sub D and Y. Which means what? We set everything to 0 except for the input that we're interested in. If we want to find the transfer function between T sub D and Y, we set R to 0, we set N to 0, and now we just compute the transfer function between T sub D and Y. Try to do that. I'll give you a minute. It shouldn't take you very long to do that. So I'm asking you to find and my writing is taking away from your minute. I want the transfer function between T sub D of S and Y of S. And if you need to work together, you may, since we're not in an exam. But I want now the transfer function between T sub D and Y. And I have already given you the answer, so I want you to show me the steps to get to that answer. Bless you. And one hint could be Mason's gain. Well, I said you could work together. That's fine. If we use Mason's gain, what are we looking for with Mason's gain? Paths and loops. How many paths are there between the disturbance T sub D and Y? One, and that's pretty easy, isn't it? We have a path. Whoa. Does that look right? That's our path between T sub D and Y. Now what do we want? You said loops. How many loops do we have? One, and it has this minus sign, and that's going to be then the product of G sub C, G, and H, which if we set H equal to 1, we can say now that our loop is minus G sub C, G, H, which we'll just go ahead and say this is equal to 1. Now what do we do with Mason's gain? Now I'm using delta in many different ways, aren't I, today? Right now I'm using it for the determinant. How do we compute the determinant of that associated with that transfer function? 1 minus the loops, the sum of the loops, and we only had 1, so we have a minus G sub C G, and I said we would maybe call that L. That's now 1 plus L. What's our cofactor? If we eliminate this path, I need to make sure my highlighter is on or I'll be really upset. If we remove that path, we've disconnected the loop, the only loop that we had, and the only thing left in our cofactor, in our determinant expression for the cofactor is going to be the 1. Which gives us then this transfer function between y and t sub d to be p y times delta 1 over delta, which is g over 1 plus L times t sub d. And that's one of the pieces of the 3 different parts that make up this equation 4.4, and that's this piece. And where did the minus sign come from? We wanted the tracking error, which is r minus y, and we computed y. We're just now subtracting y. That was a result of, or a consequence of, that disturbance input. And you can do the other 3 terms the same way to find or to derive this particular expression that gives you the tracking error as a function of the reference input, the disturbance, and the noise. Now, if we wanted to reduce the tracking error between the reference input and the tracking error, what would we do in that equation that we've labeled S? If we had freedom to manipulate that transfer function or that equation S, what would we do if we wanted to make E small when we applied a reference input? I want to make this small, don't I? The 1 over 1 plus L. How do I make that small? Can I adjust 1? No, that's a given, and it appears twice in that equation. The only thing I can manipulate is L. How do I manipulate L to make that small? Make it big. All right, so now we're concentrating, we're thinking, okay, make L big, make the loop gain big. What does that mean? In this particular example, the loop gain is the product of our controller and our plant. The plant's given. We're now saying, let's make our controller gain really big. And that might have ramifications, but right now that's what we're focused on. Let's see what now happens if we continue with that thought process. That S, the 1 over 1 plus L, that's called the sensitivity function. And L was our loop gain. And L was G sub C G. But we also had a C floating around in that equation. And what happens if we look at S plus C? It's 1, isn't it? So if I make S big, what happens to C? Has to adjust itself so that the sum is 1, right? So if S is big, C is small. This is leading us to a trade-off. If we decrease S, which I guess that was what we were trying to do, we were trying to decrease S by making L big. If we decrease S, we increase C, and that says then that we need to shape our frequency response. Maybe, because S and C are functions of frequency. And what we can think of then, if we go back here, is we hope that maybe if we wanted S small, what frequency range do we typically maybe have our reference input? What kind of signals are we trying to track? Are they changing rapidly, typically? No. And if we look at the noise, what frequencies are the noise signals typically? Higher frequencies than probably our disturbance. We have low frequency reference signals. In the lab, how often did you change the step? What was the dwell time in the lab? You kicked it, right? You kicked it how hard? 2,000. And how long did it stay 2,000? 3 seconds. Then you let it go for 3 seconds. So that's pretty slow, isn't it? That's a pretty low frequency. But our noise might be coming in at much higher frequencies. And we can use that to our benefit. If we're now looking at this waveform or this relationship, if S is small when R is important at low frequencies, maybe we make S small at low frequencies, which says make L big. If we make L big, what happens over here? It goes to 1. That means our noise goes right into our air. So we hope that we have sort of this this disconnect between when our reference inputs are active, frequency-wise, low, and when our noise is active, which is high, so that we can now make L big at low frequencies and small at high frequencies. That's this trade-off. Because our tracking error is a function of all 3 of those, and all 3 of those do impact our system behavior. All 3 of those signals: disturbances, reference, and noise. And we want to make those small. So that's relative to the sensitivity function. Let's now look at computing the sensitivity of a transfer function with respect to a parameter, which we talked about last time. Let's look at a particular example. And maybe I will label some of these blocks. Maybe I'll call this G sub 1, and this is G, and this is now our error signal. What's the transfer function between the input R of S and the output Y of S? It's a cheer, isn't it? What's our cheer? This is a little different, but just combine G1 and G. Call that G bar. What's H? 1. What's our cheer tell us? G over 1 plus GH, right? And now we're replacing G with G bar, and H is 1. So now we have G, which is G sub 1G over 1 plus G1G. That's our transfer function between the reference input R and the output Y for this expression. And we can actually compute that transfer function for the specific transfer functions G1 and G in the diagram. And we'll show that maybe we can get by without doing that, but let's go ahead and do that. There's G1. Here's G. Now we have 1 plus G1G. We can get a common denominator in the numerator and the denominator, and those then cancel, and we're left with K in the numerator over S plus alpha, S plus 1 plus K, where the S plus alpha times S plus 1 is coming because we had to get a common denominator in the denominator, which means that we're just rewriting 1 as that ratio of S plus alpha, S plus 1 over S plus alpha, S plus 1. We want to find now the sensitivity of this closed loop transfer function with respect to changes in alpha. What happens if that alpha, and that alpha is a pole, what happens as that pole moves around? How sensitive is our closed loop transfer function, T, that's the transfer function between our reference input and Y, to changes in alpha? That's what we're after or looking for. And we can actually do that a couple of different ways. And instead of just looking at finding S of T alpha directly, now that we have this expression, let's actually use something that you've learned from calculus. We love our calculus, right? The chain rule. So this is now S, the sensitivity of T with respect to G1, times the sensitivity of G1 with respect to alpha. We're really trying to break up the big problem into two smaller problems by calculating two different sensitivities. Actually, this just gives us an excuse to calculate the sensitivity twice for a problem. But what happens if we now find the first piece, the sensitivity of our transfer function T with respect to G1? Do you remember the formula for that? Partial of T, and we normalize that by the transfer function T over partial of G1 over G1, which now gives us G1T partial of T with respect to G1. And we want to now find what's in that square bracket, the partial of T with respect to G1. And I'm now suggesting that this is the expression that we want. There's T as a function of G1, G, and constants. We just need to take the partial derivative of that expression with respect to this variable G1, which is a transfer function, but that's okay. And now we can apply our quotient rule to the derivatives. We now have the partial. How do we do that? Or what do we do? Do you remember? Did everybody hear that? Clear as mud, right? We have the derivative of our numerator with respect to g1, which is g, times, well, maybe let me write it down here so that I don't have to keep scrolling. So now we had g1g over 1 plus g1g. Is that right? And now we want to take the partial derivative of that. So now we have g1, or the numerator g, times 1 plus g1g, which is the denominator, minus the numerator times the derivative of the denominator with respect to g1, which is g, over the denominator squared. And we get some cancellations in the numerator, and we're left really just with that piece. So that we now end up with g over 1 plus g1g quantity squared. That's the partial of t with respect to g1. That's just a piece of this overall sensitivity. We now need to scale that by the product of, or the division of g1 and t. Or now we have the sensitivity of t with respect to g1 is g1 over t times this partial of t with respect to g1, and that's now g1 over, t was g1g over 1 plus g1g, times g over 1 plus g1g squared. We can clean that up a little bit, and we're left then with the sensitivity of t with respect to g1 is now g1 over, whoops, let me clean it up some more. And now we have this is 1 over 1 plus g1g. Did I miss something? Does that look acceptable? And that's just the first half of our sensitivity chain rule. We now want to look at this, sensitivity of G1 with respect to alpha, and we have G1. G1 is right there. We now want the sensitivity of G1 with respect to alpha, and G1 was this K over S plus alpha. What's the expression? Partial of G1 over partial of alpha over alpha, which is now alpha over G1 times partial of G1 with respect to alpha. And again, this allows us to use, we want this piece and we can start using our quotient rule for differentiation. Denominator times the derivative of the numerator with respect to alpha. What's K? That's 0. Minus the numerator times the derivative of, or the partial of the denominator with respect to alpha, all over the denominator squared. Or this now becomes minus k over s plus alpha squared. And we can now use that in our sensitivity expression. This was alpha over G1, and G1 was k s plus alpha times minus k over s plus alpha squared. K's cancel. One of the s plus alpha factors cancel, and we have minus alpha over s plus alpha. And we can now use that to find the sensitivity of t with respect to alpha. That was the sensitivity of t with respect to G1 times the sensitivity of G1 with respect to alpha, the chain rule. What was the first piece? That was this 1 over 1 plus G1G. The last one was minus alpha s plus alpha. And if you go through the multiplication, you will find, pushing that s plus alpha factor through the denominator in the first term, we end up with minus alpha, and s plus 1 pops up, and we have s plus alpha, s plus 1 plus k. What is that? What was that? Sure. Pardon? Where's minus k? So here's minus k, and I use that right here. Is that okay? And then I multiplied by alpha over G1, and that allowed me to cancel some of the k's. But this was our sensitivity of the closed loop transfer function with respect to alpha, and now we see that this is indeed a function of frequency. How many poles do we have? 2. How many zeros do we have? Finite zeros. 1. So now, can you see the Bode plot for that particular transfer function? If I gave you some fixed values, don't be laughing at me. This should just be popping up in your mind, the Bode plot for this. If you had 2 poles and a 0, it's going to depend on where those poles and zeros are located, what the Bode plot looks like. But at high frequencies, where is this going? Where's this sensitivity expression going at high frequencies? Is it proper? Is it improper? Is it strictly proper as a transfer function? What's the order of the numerator? 1. What's the order of the denominator? 2. Is it proper? If it was proper, my fingers would have to be the same on both hands, right? And they aren't. This was numerator, this was denominator. It's strictly proper, which means at high frequencies, what's happening? S squared is dominating, isn't it? So we have S and S squared, so we have a 1 over S. What happens is frequency gets high. 1 over S. S gets big. This starts going down, doesn't it? It's getting small. We'll look at that after we do one more version of trying to compute this. Let's now look at another formula for trying to find the sensitivity of t with respect to alpha. And if you want, you should be able to find this in the textbook on page 235. Here's the sensitivity of t with respect to alpha, which last time we said you could equivalently say, oh, that's like taking the partial of the natural log of t over the partial of the natural log of alpha. But t is usually a ratio of polynomials, isn't it? T is our transfer function. So let's say we have a numerator over a denominator. And what happens when we take the natural log of a quotient? If we had a product and we took the natural log, why do we take logarithms in the first place? It helps us simplify our calculations, right? So that's adding. If we have a division, we subtract, which really says that we can now take n and d, since they're inside the argument of our logarithm, we can pull those apart and have a subtraction. We now have this is equal to the partial of ln of our numerator over the partial of ln of alpha minus partial ln of our denominator over partial ln of alpha. But those last two formulas on the right-hand side should look very familiar to us in terms of our sensitivity formula. This now says that I can find the sensitivity of t with respect to alpha by first finding the sensitivity of my numerator with respect to alpha and simply subtracting the sensitivity of my denominator with respect to alpha, and I'll get the same answer. So we've derived the general formula in this particular case, or using this t with respect to alpha. Let's apply that now to our transfer function that we had before. Our t of s we calculated was k over s plus alpha, s plus 1 plus k. We're just computing the sensitivity of that closed loop transfer function with respect to alpha a different way, and now we have to do two different computations. The first one will be the sensitivity of the numerator with respect to alpha, and the second one involves the denominator, which I'm going to go ahead and distribute that product so that I now have s squared plus 1 plus alpha s plus alpha plus k. Or if I wanted to, I could now say that that's s times s plus 1 plus alpha times s plus 1 plus k. Depending on what I want or need, maybe one of those expressions might be cleaner to take these derivatives with respect to. What's the sensitivity of the numerator with respect to alpha? That's 0, isn't it? Because there's no alpha, but let's just show that that's true. It's alpha over n times the partial of n with respect to alpha, alpha over n. We now are taking the partial with respect to alpha of k. K is not a function of alpha, so that's a simple 0. What's the sensitivity of our denominator with respect to alpha? Alpha over d, partial of d with respect to alpha. And now if we take the partial of that last formula for d of s with respect to alpha, what falls out? The factor s plus 1, just differentiating d with respect to alpha. And d was this, let's say, s plus alpha, s plus 1 plus k from before, so that it'll start to look similar to what we had before. And our overall sensitivity of t with respect to alpha is 0 minus alpha s plus 1 over s plus alpha s plus 1 plus k. that look like what we had before? Should be the same formula or expression for this sensitivity. The sensitivity, how does our closed loop transfer function change relative to variations in alpha? That's what this expression gives us. Let's see if we can start to become a little bit more comfortable with what that S of T alpha looks like. By that, let's just pick some values for alpha and K. Suppose alpha is 3 and K is 5. Maybe I'll just tell you that this choice of alpha equal 3 and K equal 5, if we substituted those back into our closed loop transfer function, they would give us a closed loop system with closed loop poles at S equal -2 plus and minus J2. Here's T of S. That was K over S plus alpha, S plus 1 plus K. We stable. And this is now 5 over S plus 3, S plus 1 plus 5. And you can see that that's now S squared plus 4S plus 8. And that factors to where we now have 5 over S plus 2 squared plus 2 squared. And why did I write it in that form? This immediately is written in a form that we can, in the S-plane, see that our poles of T of S are at -2 plus and minus J2. By that factored form. What's S? What's our sensitivity for those values of alpha and K? Our expression was minus alpha S plus 1 over S plus alpha, which is 3, S plus 1 plus 5. Or again, that's -3 S plus 1 over S squared plus 4S plus 8. That has exactly the same poles as our closed loop transfer function. Does it have anything else going on? It has a finite 0. And where's that finite 0? Can you sketch now the Bode plot of that transfer function? How far away are these poles from the origin? What's the natural frequency of those poles? It's a right triangle with equal sides, isn't it? So we now have the side times the square root of 2, so that's 2 times the square root of 2. This is our natural frequency. Omega sub n is 2 square root of 2. Square root of 2, 1.4. So this is about 2.8. It's about 3 away from the origin, 2.8. And it has a real part of -2 and a damped frequency of 2. So it will now be an e to the -2. But what does that do for us in terms of a Bode plot? What's the DC gain of that transfer function, or of this sensitivity expression? And I just want the magnitude, so I'll just take the magnitude of that. I evaluate that expression where? to get the DC value. This is the low frequency value of that expression. At 0, if I now look at the magnitude of S of T of alpha at 0, when alpha is equal to 3 and K was equal to 5, I now have minus 3, 0 plus 1 over 0 squared plus 4 times 0 plus 8, or that's 3/8. What does that tell me? If I'm sketching the magnitude of my Bode plot, yes. It is a -3, but I'm only looking at the magnitude. So I want the magnitude if I'm now doing the Bode plot. It is a minus, but we can treat that as a phase. What would a -1 look like in the phase plot of the Bode plot? 180 degrees, plus or minus. You decide, right? Typically we say let's take it minus. But now that I have the DC gain, what does that tell me? What information does that provide me in my Bode plot? Does that even help? Where we start, right? And we start, where do we start a Bode plot? Do we ever really start? That's 0, isn't it? Whoops, I'm going the wrong direction. You guys are, this is your lower frequency, isn't it? I'm sorry. I was going the wrong direction. So where do I go? All the way to Yuma? Is this what? Oh, all the way to the west coast? It's a logarithmic scale, isn't it? So it never really stops. But if we were doing it absolutely without a logarithm scale, it would be 0. But we now know what it is at that small frequency. I don't want to do this in red. This is now the magnitude of alpha of dB, and if we did that, we would take 20 log of 3/8. And that's going to be some negative value, isn't it? But it's going to be flat until what happens in this particular plot? Do we hit, what's the natural frequency of our poles? 2 times the square root of 2, 2.8, about 3. Do we get to the poles before we get to the 0? What's the frequency of the 0? Where is your 0? I thought I had it right there. It's staring at you, right? This is -1. It's at 1 radian per second. So which do we hit first, 1 or 2.8? 1. So now we hit a 0 first. What happens in our Bode plot when we hit a 0? It's upstairs, isn't it, the 0, so we're going up with our slope. And our slope, it's a single factor. What's the slope going to do? So this is now at 1, and what happens? You said we go up. How could I label that slope? Plus 20 dB per decade. And do I just keep going until New York? No. What happens? You hit a double pole, basically, don't you, the way we did it in 320. And where is that located? Where was the natural frequency of that pole? 2.8. So now we're at 2.8. And now what happens? Do we stay flat? Do we go up? Do we go down? We go down at minus 40 dB, but we were going up at plus 20, so we come down at a net. Ooh, that's supposed to be a straight line. Of minus 20 dB per decade. That's the magnitude of this sensitivity. Where is it most sensitive? At what frequencies? At 2.8. So now if you had certain signals or something happening at 2.8, you know your system is quite sensitive at that frequency range. Let's just give yourselves a pat on the back by going and looking what would happen if we sketch this sensitivity with MATLAB. So here's our transfer function, minus 3s plus minus 3. We do the transfer function operation. We do the Bode 1 command. Does that look sort of like what we just sketched? Where does it start bending up? 10 to the 0, 1. Where does it start coming down? This is 2. This is 3. It better be a little bit below that. It's pretty good, isn't it? And is it going down as we keep going to higher frequencies? Give yourselves a round of applause, and we'll pick up at that point on variety. Wow.